In section 3.3, we're going to look at algebraic ways to evaluate limits. So the first strategy we have for evaluating limits is direct substitution. So say we're asked to find the limit as x approaches 5 of x squared plus 2x minus 3. Well, I can directly substitute 5 in for x, provided I do not get a value that is undefined. So if I put a 5 in, I end up getting 25 plus 10 minus 3. This limit works out to be 32. So therefore, the limit as x approaches 5 of this function is 32, which means as x approaches 5 on the graph of my function, the y values from both the left and the right are approaching 32. The limit as x approaches 1 of x to the fourth minus 5x squared plus 1 over x plus 2. Again, if I use direct substitution, I'm substituting 1 in for x, and in this case, I'm going to get 1 minus 5 plus 1 is going to be negative 3 over positive 3, which is negative 1, and therefore that would be my limit. So plugging in 1 did not cause me to get an undefined value or a 0 in the denominator, so therefore I can use, again, direct substitution. Similarly, in this example, if I plug in a 3 into my function, I end up getting 3 squared plus 3, which is going to be the square root of 12, which reduces to be 2 root 3. And therefore, as x approaches 3, the graph of my function, both from the left and the right, the y value is approaching 2 root 3. Looking at our next example, the limit as x approaches 9 of log base 3 of x all over sine pi x of 18. So again, if I use direct substitution, I'm going to get log base 3 of the number 9 over sine of 9 pi over 18. Again, I purposely chose this one to review some of our concepts from pre-calc 30. So log base 3 of 9, we have a couple of ways to solve that. One way is we can make this equal some variable. I'll use a different variable because we used x in the question. Let's call it m. And we're going to convert this to exponential form. So if you remember from pre-calc 30, I take this base and raise it to the value on the other side of the equal sign, and it has to equal the number within my logarithm. So now I'm going to get both bases the same. And since both bases are 3, the exponents have to equal. So therefore, log base 3 of 9 is going to equal 2. And figure out sine of 9 pi over 18. This is really sine of pi over 2, which is really the sine of 90 degrees. If you remember your unit circle from pre-calc 30, 90 degrees is right here. And on the unit circle, the coordinate of that point would be 0, 1. So this angle here is pi over 2. And remember, the sine of any angle on the unit circle is really the y coordinate of its point on the unit circle. So therefore, the sine of pi over 2 is really equal to 1. So this answer is going to be 2. The other way you can think about the sine of pi by 2 is you can think about the sine graph. And notice, remember, sine starts at 0. At pi over 2, it's up to 1. And then at pi, it's back down to 0. And so the graph goes like this. It does continue. But at pi over 2, the y value is at 1. So that's another way of evaluating the sine of pi over 2. So basically, if our function is a polynomial, we can use direct substitution. If our function is rational or algebraic, we can also use direct substitution, provided it doesn't make our function undefined. Now, how do we evaluate one-sided limits? Okay, so we are given a question here. The limit as x approaches negative 4 from the positive side, from the negative side, and just at negative 4 of x plus 6 over x plus 4. Okay, so we're just going to analyze this one, and I'm going to show you a technique, and we'll be able to answer all 3 of these questions just by doing part C. So first of all, we're asked to find the limit as x approaches negative 4 of x plus 6 over x plus 4. If I was to use direct substitution, I would get negative 4 plus 6 over negative 4 plus 4, which gives me a number over 0, which means, back from our study back in section 1.3, is that negative 4 makes this function undefined. Therefore, x equals negative 4 is a vertical asymptote. Again, if you substitute something in and you get a number over 0, that means that that number is a vertical asymptote. Now, if you think of a vertical asymptote, so we know we have a vertical asymptote at -4. As my graph approaches the vertical asymptote, it can either go up or it can go down. So the answer to this limit is either going to be infinity or negative infinity. Okay, so the easiest way to do this, I'll just start a new page. So we have the limit as x approaches -4 of x plus 6 over x plus 4 is to do a little number line. So on my number line, you're going to place the value that makes the bottom 0, which is going to be -4. And I'm going to put a infinity there to indicate it's undefined. And we should think about what makes the numerator 0, and that's going to be -6, and I'm going to choose a 0. So now we want to figure out the limit as x approaches -4. So we're concerned about this area here. So we're going to take a number in this interval and a number in this interval. Okay, if I plug -5 into this expression, -5 makes the top positive because -5 plus 6 is positive, and -5 plus 4 is negative. A positive by a negative is going to be a negative. And as I approach -3, if I plug in -3, sorry, I get a positive over a positive, so it's going to be positive. And I'm just going to switch these around because it might make more sense if you see it this way. So again, we use -5 and -3, and it was plus and negative. So now, the limit as I approach -4 from the right side, well, I have a plus sign on the right side of my infinity sign. So that means as I approach -4 from the positive side, the graph is going up. It's going to positive infinity. As I approach -4 from the left, I have a negative sign on the left, which means the graph is going down forever and ever. So it's going to negative infinity. Therefore, the limit as x approaches -4 for our textbook would say does not exist because the limit from the left does not equal the limit from the right. So a number line test or a sign chart, some books refer this to, is sometimes the easiest way to figure out limits at vertical asymptotes. Okay, this time here we're asked to find the limit as x approaches 3 from the left side. So if I approach 3 from the left side, okay, if I plug 3 in, I'm going to get 3 over 3 minus 3 all squared, which is going to be 3 over 0. Therefore, I know that x equals 3 is a vertical asymptote. Now I can go straight to my number line. And what makes the bottom 0? That's going to be when x is 3, so that's going to be undefined. And the value that makes the top 0 is going to be 0. And I'm concerned about the limit as x approaches 3 from the left. So let's figure out, I'll take a number to the left of 3 and a number to the right of 3 and plug it into here. Well, no matter what I plug into the bottom, when I square it, it's going to be positive. So a positive divided by a positive is going to be a positive. Positive divided by a positive is going to be a positive. This question is only asking me for the limit as x approaches 3 from the left. So on the left of 3, I have a plus sign beside my infinity. So this graph is going to towards positive infinity. Okay, let's try this one here. In this example, they're asking me for the limit as x approaches 4. It's not giving me one side to check, so therefore I must, first of all, plug 4 in to see what I get. If I plug 4 in, I get 4 over 3, which is going to give me 7. And I'm going to get 4 squared minus 2 times 4 minus 8. So I'm going to end up with 7 over 0. So therefore, x equals 4 is a vertical asymptote. So therefore, I have to go to my sign chart. But before I go to my sign chart, I'm going to factor the denominator, because the denominator factors into x minus 4 and x plus 2. So therefore, on my number line, I'm going to have -2. So that makes this guy 0. He's going to be an undefined. 4 makes this guy 0. He's undefined. And -3 makes the numerator 0. Now, I'm only concerned about what's going on in this region here because I'm asked for the limit as x approaches 4. So let's take a test point to the left, like 3 and 5. If I plug 3 in the numerator, it's positive. 3 in here is positive. 3 in here is negative. 2 positives and a negative is going to make this interval negative. If 5 makes all three of these factors positive, so it's going to be positive. So coming from the left of 4, the graph would be going to negative infinity. Coming from the right of 4, it would be going to positive infinity. So at 4, this limit does not exist. Okay, in our last example, we're looking at a piecewise function, and we're asked to solve this one algebraically. And we are asked, first of all, to figure out the limit as x approaches -3. Well, -3 belongs in this domain. So the first thing we're going to do is we're going to rewrite this limit. And in place of my function, I'm going to put the function that belongs to that domain, which is going to be x squared. So now if I use direct substitution, this limit is going to be 9. The next example is the limit as x approaches 5, and 5 fits into that domain. So therefore, I'm going to rewrite this function. So the limit as x approaches 5 of 2 minus x. Direct substitution is going to result in a limit of -3. Now the last example, or last part, you have to be careful, because this is a limit as x approaches 1, and 1 is where the function changes behavior. So left of 1, it is x squared. Up to the right of 1, it's 2 minus x. So to figure out if there's a limit at 1, we have to determine the limit as x approaches 1 from the left and the limit as x approaches 1 from the right. As I approach 1 from the left, I'm using the function x squared. Using direct substitution, 1 squared is going to be 1. As I approach 1 from the right, it's bigger than 1. I'm going to use the function 2 minus x. If I plug a 1 in, I also get 1. So the limit from the left of 1 is 1, from the right of 1 is 1. So therefore, the limit as x approaches 1 is 1. Now, if these two limits were not the same, we would say the limit here does not exist. Okay, so there's some questions for you to try. All right, if you have any questions, the answers for these are on the website, so give those a try and see how you do.